Today we will discuss different instructions used in SAP2. Memory reference instructions. The SAP2 fetch cycle is the same as for SAP1. T1 is the address state, T2 is the increment state, and T3 is the memory state. All SAP2 instructions use the memory during the fetch cycle. Because a program instruction is transferred from the memory to instruction register. During the execution cycle, the memory may or may not be used. A memory reference instruction MRI is one that uses the memory during the execution cycle. The SAP2 computer has an instruction set with 42 instructions. LDA and STA. LDA means load the accumulator. Load the accumulator with the contents of given memory location. So it is memory reference instruction. Now the addresses are from 0000H to FFFFH. LDA 2000H means load the accumulator with the contents of given memory location 2000H. Other instruction is STA. STA means store the accumulator. Every STA instruction needs an address. STA 7FFFH means to store the accumulator contents at memory location 7FFFH. If A equal to at AH, A is accumulator content. If it is at A in hexadecimal number system, the execution of STA 7FFFH stores at AH address to at address 7FFFH. Next instruction is MVI. MVI means move immediate. It tells the computer to load the designated register with the byte that immediately follows the operational code. For example, MVI A37H. This tells the computer to load the accumulator with 37H. It is not the address of memory location, it is a byte. 4 bits for 3 and 4 bits for 7. So it is a byte, it is a word of 8 bits. MVI A37H, this instruction tells the computer to load the accumulator with 37H. After this instruction has been executed, the binary contents of the accumulator are then accumulator A now becomes equal to 00100111. It is loaded with this byte 37H. Left side 4 bits are for 3 and right side 4 bits are for 7. So it is 37 in hexadecimal number system. We can use MVI instruction with the A, B and C registers. The formats of these instructions are MVI A, byte, MVI B, byte, MVI C, byte. Register instructions. Memory reference instructions are relatively slow because they require more than one memory access during the instruction cycle. SEP2 register instructions are used to it must be execution cycle here instead of instruction cycle. Memory reference instructions are relatively slow because they require more than one memory access during the execution cycle. SEP2 register instructions are used to move data directly from one register to another without using memory. So these instructions are executed much faster than memory reference instructions. MOV. MOV is mnemonic for move. It tells the computer to move data from one register to another. For example, MOV A, B. This instruction tells the computer to move the data from B register to the accumulator. Note the order. MOV is for move A, B. This moves the content of B register to A register, accumulator. Move A, B tells the computer to move the data from the B register to the accumulator, that is A register. In this operation, data in B register is copied but not erased. If A equal to 34H and B equal to 9DH, then the execution of MOV A, B results in A equal to 9DH, that is content of B register, and B equal to also 9DH, which is already there. So content of B register is copied and it is moved to A register, and now content of A register is changed and it will become the same as that of B register. We can move data between the A, B and C registers. The format for all move instructions are MOV A, B, MOV A, C, MOV B, A, MOV B, C, MOV C, B. These instructions are the fastest instructions in the SEP2 instruction set and require only one machine cycle. add and sub. Add ADD stands for add the data in the designated register to the accumulator. For example, add B means to add the contents of B register to the accumulator. If A equal to 0 for H and B equal to 0 to H, then the execution of add B results in A equal to 0 6 H. A is 0 for H, B is 0 to H, so A plus B will be equal to 0 6 H. So execution of add B will add the content of B register to the content of accumulator, and then accumulator content becomes A equal to 0 6 H. That is the addition of contents of A and B registers. Similarly, sub means subtract the data in the designated register from the accumulator. Sub C will subtract the contents of the C register from the accumulator. The formats for add and sub instructions are add B, add C, sub B, sub C. INR and DCR. INR is mnemonic for increment. INR for increment and DCR for decrement. So INR, that is for increment, it tells the computer to increment the content of designated register. DCR is mnemonic for decrement. It tells the computer to decrement the content of designated register. The formats of these instructions are INRA, increment A, INRB, increment B, INRC, increment C. Similarly, DCRA is for decrement A, DCRB for decrement B, DCRC for decrement C. For example, if we have B equal to 5 6 H and C equal to 8 AH, then execution of INRB, increment B, will result in B equal to 5 7 H. Since B is 5 6 H, if it is incremented by 1, then INRB increment B will result B equal to 5 7 H. And if C is 8 AH and we have instruction DCRC, decrement C, then content of C will be decremented by 1 and execution of the instruction DCRC will result C equal to 8 9 H. If initially C equal to 8 AH, then decrement C, DCRC will result C equal to 8 9 H. If A is decremented by 1, it results in 9. hexadecimal numbers are from 0 to 9, then A, B, C, D, E, F. After 9, A appears in hexadecimal number system. So before A, it will be 9. So if 8A is decremented by 1, it will result 89 in hexadecimal number system. Jump and call instructions. We will first discuss jump instructions. SAP2 has 4 jump instructions. These can change the program sequence. Instead of fetching the next instruction in the usual way, the computer may jump or branch to another part of the program. So SAP2 has 4 jump instructions, and these can change the program sequence. Instead of fetching the next instruction in the usual way, the computer may jump or branch to another part of the program. Out of these 4 jump instructions, first is JMP. JMP is mnemonic for jump. It tells the computer to get the next instruction from the designated memory location. Every jump instruction includes an address that is loaded into the program counter. For example, JMP jump 3000H. This jump instruction tells the computer to get the next instruction from memory location 3000H. Suppose JMP 3000H is stored at this memory location 2005H as shown in figure A. This is figure A. In left side, we have written different memory locations starting from 200. These memory locations start from 0000H to FFFFH. Some of these memory locations are shown in this figure. These are started from 2000H. Then these hexadecimal address are incremented by 1. We have shown here 2 other addresses, 2005H and 2006H, and after that 3000H is shown. So these are addresses of memory locations, hexadecimal addresses. Of 16 bits. So in this figure we see that in the memory location 2005H, the instruction is JMP 3000H, jump 3000H. So this instruction JMP 300H, this instruction tells the computer to get the next instruction from memory location 3000H. Suppose JMP 300H is stored at 2005H as shown in this figure. At the end of fetch cycle, the program counter contains program counter PC equal to 2006H, After 2005H, we have 2006H, and during the execution cycle, the jump 3000H loads the program counter with the designated address, and now program counter becomes 3000H. When next fetch cycle begins, the next instruction comes from 3000H rather than 2006H. So if at memory location 2005H we have jump instruction, jump 3000H, then it will jump to the instruction of memory location 3000H. JM. SAP2 has two flags, sign flag and zero flag. During the execution of some instructions, these flags will be set or reset depending on what happens to the accumulator contents. If the accumulator contents become negative, the sign flag will be set, otherwise it is cleared. Reset. Symbolically, S. S stands for sign flag. S is 0 if A is greater than equal to 0. That is, if A is 0 or positive, this sign flag S is 0, it is clear or reset. And this sign flag is set, means sign flag S equal to 1. It means it is set if it is not A equal to 0, it must be A less than 0. A less than 0 means A is negative. So if accumulator content A is negative, A is less than 0, then S equal to 1, sign flag is set. So when accumulator content becomes negative, A becomes less than 0, then sign flag is set and S equal to 1. So correct here, S equal to 1 if A is less than 0, it is not A equal to 0. Here S stands for sign flag. The sign flag will remain set or clear until another operation that affects the flag. JM is mnemonic for jump if minus. J for jump, M for minus. So this is also jump instruction. JM, jump if minus, the computer will jump to a designated address if and only if the sign flag is set. Sign flag is set. It is set when accumulator content becomes negative. Suppose JM3000H is stored at 2005H. This is shown in figure B. At memory location 2005, now stored instruction is JM3000H. JM means jump if minus. if accumulator content A becomes negative, then jump to 3000H. Suppose JM300H is stored at 2005H. At the end of fetch cycle, the program counter PC becomes equal to 2006H. If S equal to 1, sign flag is set, that is when accumulator content is negative. Then during the execution cycle, the JM300H loads the program counter with program counter will become 3000H. So program counter now jump to the instruction at hexadecimal address 300H. If sign flag is set, it will not take instruction from the hexadecimal address 2006H. It will jump to the instruction at hexadecimal address 300H. Because accumulator content is minus, sign flag is set. So JM300H, this instruction leads that it will jump to the instruction at memory location 300H. And now if accumulator content is not minus, A is 0 or positive, then it will not jump to 300H. It will jump to 300H only when accumulator content is minus. Sign flag is set. If S is equal to 0, sign flag is clear. The program counter is unchanged during the execution cycle. When the next fetch cycle begins, next instruction comes from 2006H. Figure B shows the two possibilities for JM instruction. If sign flag is set, the counter jumps to 300H, and if sign flag is clear, the next instruction comes from 2006H. Next jump instruction is JZ. J for jump, Z for 0. During the execution of some instructions, the accumulator will become 0. If the accumulator contents become 0, the 0 flag will be set, otherwise it is cleared, reset. So 0 flag, Z is for 0 flag, and if Z is 0, A is not 0, and if accumulator content A equal to 0, then this 0 flag is set, that means Z is 1. So Z equal to 1, it is set, 0 flag is set, Z equal to 1 only if accumulator content becomes 0. Otherwise, if A is not 0, it is reset or clear, Z is 0. Here Z stands for 0 flag. The 0 flag will remain set or clear until another operation that affects the flag. JZ is mnemonic for jump if 0. If accumulator content is 0, then jump. Jump if 0, JZ, jump if 0, jump if accumulator content is 0. The computer will jump to a designated address if and only if 0 flag is set, that is when A is 0, accumulator content is 0. Suppose JZ300 H is stored at 2005H. At the end of fetch cycle, the program counter contains PC equal to 2006H. If Z equal to 1, 0 flag is set. Then during the execution cycle, the JZ300H loads the program counter with program counter now becomes 3000H. If Z is 0, 0 flag is not set, it is reset. The program counter is unchanged during the execution cycle. When the next fetch cycle begins, next instruction comes from 2006H. And the fourth jump instruction is JNZ. JNZ stands for jump if not 0. In this case, we get a jump when 0 flag is clear and no jump when it is set. J and Z jump if not 0, if accumulator content is not 0, and accumulator content is not 0, it means that 0 flag is clear, it is reset. Suppose a JNZ 7800H is stored at 2100H. If Z equal to 0, 0 flag is reset, A is not 0. The next instruction will come from 7800H. JNZ 7800H jump if accumulator content is not 0 and Z means not 0. Jump if not 0, J and Z jump if accumulator content is not 0. So if accumulator content is not 0, it means 0 flag is clear. Then it will jump to this instruction at this address 7800H. If Z equal to 1, 0 flag is set, A is 0. The next instruction will come from 2101H. After 2100, the next instruction will come from 2101H. JM, JZ and JNZ are called conditional jumps because the program jump occurs only if certain conditions are satisfied. JMP is unconditional because once this instruction is fetched, the execution cycle always jumps the program to be specified address. So JMP jump instruction is unconditional, while other three jump instructions, that are JM jump if minus, JZ jump if 0, and JNZ jump if not 0, these are conditional jumps, and program counter jump only these certain conditions are satisfied.